Hi, this is Mr. Mitchell. I'd like to do a video on acceleration. Acceleration reflects a positive change in speed, and in reality, almost every motion includes some kind of acceleration or deceleration. It's very hard to get constant speed. For example, if this person is running in a race, they're going to have to start at 0 meters per second. They are not moving at the start. So most likely after they start, they will be running at some kind of rate which will be a little faster, and then by the time they get to their maximum speed, it will be even higher than that. They are accelerating throughout to a certain point when they are reaching their maximum speed. So you have acceleration with almost every bit of motion, and you can easily see acceleration on a distance time graph. When the graph curves up, you have some kind of acceleration. Now there can be negative acceleration. Now negative acceleration doesn't mean somebody's going backwards. Negative acceleration means somebody is slowing down. And in this particular frame, we just have this person who is speeding up. Same thing right here. You see the graph going up. That means that whatever is being recorded is speeding up. Now there happens to be a formula for acceleration. The formula is final velocity minus initial velocity. Believe it or not, that's what the O means, over time. In other words, change in velocity over change in time. That's probably an easier way to remember it. So let's look at this graph. This is the same graph we had in a different video where we looked at 3 seconds in. The person or whatever it was that's being recorded had gone 10 meters. And we had that was 3.3 meters per second. But notice we had this way down at the end. They had gone after 10 seconds, they had gone 100 meters. So you had a faster rate of speed the farther along time went. So that is classic acceleration. But why don't we put a figure to that? Here I have the acceleration formula, and I have already put in some of the numbers. We had 10 is the number of meters per second that we had. That was the final velocity. At the end, it was 10 meters per second. The initial velocity, we'll just start right here since we picked a place on the graph. Yes, we could have picked another place. We could have picked 0, we could have picked 5, but we have a different rate of acceleration throughout all of these. So I decided just to pick here for the sake of our calculation. So we had 10 meters per second minus 3.3 meters per second over the change in time, which in this case we went from 3 to 10, so that is a total of 7 seconds. So in that case, it's just a matter of punching it in the calculator, and I happen to have already done that, and it would be 0.96. And I want you to pay attention to the unit here. We have meters per second at the top of the fraction, and we have seconds at the bottom of the fraction. I'm going to move it down here because we might not have enough space, but that means that acceleration is in meters per second square. Yes, meters per second square is not as easy to grasp, but that's what it happens to be. You have an acceleration in meters per second is maybe a way you can wrap your head around that. For every second after 3 seconds, the acceleration is 9.6 meters per second. For every second after that, it's 9.6 meters per second. So it's over and over. So that is meters per second square. Now, we mentioned something called deceleration earlier, that it was not running backwards, it was just slowing down. For example, if the runner had gotten to 3.2 meters per second, fatigue is going to kick in at some point, and they will start slowing down. So let's say for the next 2 seconds, they ended up slowing down to 2.8 meters per second. And you can probably imagine what that would look like on a distance time graph. While acceleration was going up on the graph, deceleration is going down. And that's probably an exaggerated going down. This woman right here is not going to go down that far on the graph. But if you just look at the graph, you'll be able to see what is going faster, acceleration, and what is going slower in deceleration. So we could even calculate the rate of deceleration here. as we have change in velocity over change in time. 2.8 is the final velocity, 2.8 meters per second square, and 3.2 is the initial velocity. So notice you're going to end up with a negative number. So one thing to note is that anytime you have negative acceleration or deceleration, you're going to have a negative number. Anytime you have positive acceleration, of course, it will be a positive number. So you ended up with 2.8 minus 3.2 is going to be 0.4 meters per second over 2 seconds. So in that case, it's just a matter of dividing it out, and that will end up being, I think I probably should be able to get this on my own, but I'm going to put this in the calculator. 0.4 divided by 2 equals, and that will be negative 0.2 meters per second square. Negative 0.2. Oh, and I don't give myself much space here, do I? Negative 0.2 meters per second square. So you do have negative calculations because you have deceleration that you're calculating sometimes. Did you know that when things are falling, that they accelerate, that they gather speed as they fall? For example, here at the bottom we have a lady on top of the cliff, and she has her cell phone, or at least my picture of a cell phone here. If she were to drop that cell phone, it would speed up as it goes down. It gets faster and faster as it falls. Now, everything on Earth accelerates at the same speed whenever it is falling. Now, I say everything. There are exceptions, like feathers or things that have wind resistance against it. And there's another exception with altitude, but we have a steady rate of acceleration when it comes to falling objects. So something kind of an interesting note is that you do have a falling acceleration, whether it's a cell phone, whether it's a penny, or whether it is anything that doesn't have much wind resistance. You're going to have 9.8 meters per second square. That will be the rate of falling acceleration. And you know, in class we'll do some acceleration problems, and this is how you do them. Hope you learned a lot. Thank you.